Hello. Quick video on using Poisson probabilities to approximate binomials. Historically, it's on occasions been easier to calculate Poisson probabilities than binomial, particularly in the days before we had calculators. And it's possible to do this when we've got binomials that look very much like Poisson, a bit like the one I've got in the diagram here, where the probability of something happening is very low and there's a large number of trials. So we've got this very skewed distribution. Okay, so just to take us on, have a quick look. Here we go. Poisson to binomial. So what do I mean by very large? Well, we mean that the n is greater than 20. Our p is less than 0.7, and NP is not large, so it's typically in the region 1 to 10. So in those circumstances, we'd have a graph, the distribution looks like this. So here's our example with n equals 50 and p equals 0.05. So we've got a very skewed distribution towards the left-hand end. We've got a very narrow peak, only a very limited number of probabilities that actually look like they're going to actually have any meaningful probabilities. Right over here, isn't it? And a mean right down here. Yeah, not like this one here where our p is 0.5. So 0.5 that's a very symmetric diagram, isn't it? It doesn't really look like a Poisson at all. Okay, let's do an example. Let's have a look at a disease. So let's say that in our society there's a disease which affects 1 in 40,000 of the population. And in a small community of 60,000 people, we find that there are 5 sufferers. The question is, how unusual is that? So what's the probability of 5 or more sufferers in a community? Well, what we're looking at here is a binomial, isn't it? You either have the disease or you don't. And if we looked at that, well, our n would be 60,000, our p would be 1 in 40,000, and we'd be interested in probability that x is greater than or equal to 5. So does this fit the criteria we've set? Yes, it does, because n is 60,000. That's much more than 20 that we talked about on the last slide. That's large. We could say very large, and p is 1 in 40,000. Well, that's much less than 0.1, and that's small, isn't it? Well, that's very small. Okay, what's our NP value? Well, that's our 60,000 times by 1 in 40,000. 1/4 as a fraction, and that gives us that we should be seeing 1.5 people with this disease in the community. So that's not large, so that's all okay, isn't it, to apply it? Okay, how do we convert our binomial into a Poisson? Well, we need to work out what the mean is for our Poisson, what our rate is, our lambda. And the mean of the binomial is going to be NP, which we worked out to be 1.5. So we're going to use Poisson with a lambda of 1.5. There we go. And we are going to work out our probability. Usual way, probability that x is greater than or equal to 5. Well, we know in our calculators will only give us a less than or equal to. So therefore we have to use our complementary probability. So the probability of greater than or equal to 5 is the same as 1 minus the complementary probability of x being less than or equal to 4. And if we go to our calculators, our life becomes very easy to work this out. Excuse me, getting back up. Exit. Come on, where have I got to? Distributions. Here we're interested in our Poisson distribution. We're interested in our PCD, and we're going to calculate, our x value we're looking for is 4, our target value. Our mean here we're going to use is 1.5, and hey presto, our probability here of that, if the complementary is 0.9814, here we go, 0.9814, 1 minus that gives us a probability of 0.186. We're not surprised about that, are we? Because it's a very low occurrence of having 5 people. So that's very unlikely to have happened. Okay, just to check how accurate, how precise that is, let's use our binomial. If we went into our calculator and used the values 60,000 for n and 40,000 for p, so let's do that. Exit, here we go, distributions, binomial, BCD. Let's put in there's our target 4. Our number of trials is 60,000. Our P is 1/40,000. That comes to that value there. And we're going to get 0.9814. So we've got exactly the same number, haven't we? Well, we would expect it to be pretty accurate because our N is very high and our P is very low. Okay, so quick summary then. We can use our Poisson to approximate a binomial where the binomial is very skewed like a Poisson. For that to happen, we need a large n greater than 20, a p of less than 0.1, and an np that's not large. And if we get if those conditions are met, we can use our Poisson, and for our lambda we need a mean rate. We're going to use our binomial mean. That's our NP. So there we are. I hope that's of use.